This video is for lesson 8-6 about hyperbolas. So we've recently discussed shapes that are defined in terms of distances. We looked at a circle, parabola, and ellipse. And now we'll get our last shape that we're going to look at in Algebra 2 class. This is called a hyperbola. It is the set of points such that for each point, the absolute value of the difference of its distances from two given points is a given constant. The hyperbola is different from an ellipse because it involves the difference of two distances, whereas an ellipse was the sum of two distances. Let's look at an animation of a hyperbola. The figure shown in blue ink is a hyperbola. Notice that it is made out of two branches. A hyperbola has 2 points called foci, just like an ellipse does. And in this animation, we can control where the foci are located. For instance, I can click this and drag it further to the left. Notice what's happening to the distances between the foci and point P, which is right here on the parabola. When you subtract the distances, it remains a constant number. So as I move this one out here farther, this one here gets a little bit longer, so that when I subtract the two distances, I'm always getting a constant amount. Have you also noticed that as the foci gets further from the center point between the blue hyperbolas, that the branches of the hyperbolas widen out? Let me move foci 1 closer to the center point between the two blue hyperbola branches. Notice what's happening to the shape of those blue curves. They're narrowing. This animation shows hyperbolas whose foci are on the x-axis. But hyperbolas can also exist where the foci are on the y-axis. Let me move that one there, and this one down here. Look what happened to the hyperbola branches. Now one of them opens up, and the other opens down. So like an ellipse, which can stretch longer sideways than tall, or it can be taller than it is wide, hyperbolas have two basic orientations as well. Let's go back to the notes. If point P represents any point on a hyperbola that has foci at this spot and this spot, then the focal radii differ by 6 units. The numbers are filled into the distance formula, and some simplification is done. After simplifying, the equation that you get for that hyperbola looks like this. So this suggests a general form for equations of hyperbolas. Notice it has x squared on top, y squared on top. That's just like ellipses. It has a denominator here, a denominator here. It has a 1 on the right side, all just like ellipses. But look at the thing that's different. There's a subtraction sign. Let's graph that hyperbola on this grid. Looking at the denominator under x squared, we can figure out that a is equal to 3. Looking at the denominator under the y squared, we can figure out that b is equal to 4. Now, what is the meaning of those numbers when we have a hyperbola, not an ellipse? From the center, on the x-axis, go 3 units left and mark it with a dot, and go 3 units to the right and mark it with a dot. On the y-axis, go up 4 and mark it, and go down 4 and mark it. If this was an ellipse, right, if this had a plus sign in the middle, we would then draw in an oval shape. But that's not what we're going to do to make a hyperbola. Instead, lightly or with dashed lines, draw a vertical line through that x-intercept spot. Then, draw a horizontal line that goes through that number we marked on the y-axis. Then, go vertical again and go through the 3 on the x-axis. And then draw across through positive 4 to complete a box shape. Now, why did we do that? We're now going to draw the diagonals of that box shape. So lightly, or using dashed lines, draw from corner to corner. And it's going to go through the origin as you do this. And then the other diagonal. Again, when you're doing this with pencil on paper, you want to either draw lightly or you can use the dashed lines. We've done all of this work to help us make the hyperbola. And now we're going to actually draw the hyperbola. It will touch the x-axis at the dot that we marked here at -3. And it will swing up and then alongside that dashed diagonal line. The same thing as you draw the branch coming down here. Come up close to that diagonal dashed line without touching it. There's a word for that we actually had earlier this year. It is called an asymptote line. An asymptote is a line that a function gets closer and closer to, but never actually touches. Now, how do you make the other branch of the hyperbola? It's going to touch this dot that we marked at 3. And it's going to swing up like this and then get closer and closer to that diagonal dashed line. And the same coming down here. So our hyperbola actually consists of these two red curves that cross the x-axis at -3 and at +3 and get closer and closer to these dashed diagonal lines that we drew, which are called asymptotes. Once you've drawn the curves in, you can take an eraser and erase away that rectangular box. What you don't want to erase away, though, are the dashed lines called asymptotes. Because when you draw curves that have asymptotes, the accepted technique is to leave the asymptotes in the picture using dashed lines for them. So we looked at a specific hyperbola that actually had numbers. Now let's look at the general forms. When the foci are on the x-axis, here's the general form. The x squared term will be written first, and there will be some kind of denominator. The y squared term will be written second, and it'll have some kind of denominator. There'll be a 1 on the right side, and there will be a minus sign. Remember, if it's not a minus sign, if it's a plus sign, what shape is it then? It's an ellipse. Well, what about the other hyperbola? When one of the branches goes like this, and the other branch goes like this. That's when the foci are on the y-axis. So look how the equation's different. It's the y term that's first, and then the x term is after the subtraction. The technique that we use to draw the hyperbola by hand is called the box method. So these steps here describe out how to do the box method. Marking dots on the x-axis and on the y-axis, drawing a rectangular box, and then drawing the diagonals, which end up being the asymptotes. Let's try another example. Here we have a quadratic equation. It has an x squared and a y squared. So because of that, it's not a parabola. Now, is it an ellipse or a hyperbola? It has subtraction, so I'm thinking it's probably a hyperbola. Let's make standard form. In standard form for a hyperbola, it's equal to 1. So let's divide by the -144. That'll make a 1 on the right side. We will get 16x squared over -144 minus 9y squared over -144, and that's equal to +1. This isn't quite the format that we want yet. We don't want to have a coefficient in front of the variable in the top. We only want to have a number in the bottom. So let's reduce the 16 over 144. They both divide by 16. This makes negative x squared over 9. Now in this spot here, negative divided by negative makes positive. Let's reduce the 9 over 144. They both divide by 9. We're left with y squared over 16, and that's equal to 1. Is this the format we're looking for yet? How do we fix it? Let's reverse the terms. Put the y squared over 16 first, and then put the minus x squared over 9. Now we have the general form for a hyperbola. The term with y comes first, so what's its orientation? Is it the kind that goes side by side, or the kind that is like the up and down? What's the orientation when y comes first? It's that second one. Okay, using square roots, we see a is 4 and b is 3. So on the y-axis, go up to 4 and mark it, and go down to -4. On the x-axis, go to -3 and +3. Now what do? Draw a box. What do you do next? Draw the diagonals of the box. And what do you do next? Now you draw in the branches. So going through 4 and swinging close to that asymptote line, and then coming like this and getting close to the asymptote line. Don't forget the other branch down here. The actual answer are the two curves. All of that other stuff is just the work that you do to help you get it on paper accurately. Another example. Let's graph this one. Well, what is it? It has x squared and y squared. So is it a circle? Is it an ellipse? Or is it a hyperbola? It's got a minus sign. So it's a hyperbola. It already has the equals 1. We just need to pay attention to the denominators. I guess they're both 1s. Using square roots, we get a equals 1 and b equals 1. Because remember that this is a squared. And remember that this number is b squared. Now what do? You decide on the orientation. The x squared comes first, so it's the kind that looks like this. So on the x-axis, go 1 unit left, 1 unit right. And on the y-axis, go 1 unit up, 1 unit down. Draw a box. Then what do? Now you draw the diagonals of the box. After you draw the asymptotes, now you can make the actual hyperbola. So it goes through this dot, and it comes up close to the asymptote, and then swings down next to this asymptote. Over here, it's going to go through this dot, and come up close to that asymptote, and down here, it'll get up closer and closer to the asymptote as you go. Notice it's very important to pay attention to orientation, because even if you make all the diagonal lines, you still have to decide whether the hyperbolas go in the left and right sections or whether they fit in the top and the bottom sections. Let's summarize the lesson. We explored how to graph another geometric shape called a hyperbola, and we looked at the general form for a hyperbola, which looks a lot like an ellipse, but it has a minus sign in it. In one of our questions, the equation was not in the correct form to begin with, and so we rearranged it so that it had equals to 1 on the right side.